Welcome everyone. We're at the last part of the course, so congratulations. Now we just want to cover some biomolecule stuff, which is really helpful if you're going to take biochemistry. And for those of you who are taking it right now or finished it, this should be a breeze, right? But this is all going to be sort of applied to organic chemistry and some of the reactions we've learned. So it will tie back into what you've learned this quarter. My goal is to provide you with some of the basics of biochemistry, just structurally, carbohydrates, lipids, proteins, and nucleic acids. I want to make this as painless as possible because it's the end of a tough quarter, a lot of reactions and mechanisms, and this section is really just for you to get some understanding about how these molecules apply to life. There's normally a lot of memorization for you to look at all these structures, but for my class, I'm just going to run it through and have you guys do an assignment where you use these things, and then hopefully when you take biochemistry, you'll have a better understanding, and then you'll be able to memorize a lot of it then. Okay, so for now, we're going to start with carbohydrates, and the idea of where that word comes from is actually hydrates of carbon. So if you look at a carbohydrate, which is basically sugars, if you look at the chemical formula for many sugars, they end up having this kind of pattern to them, which is CnH2ON. And so these are hydrates of carbon, so carbohydrates. And I can do a crazy reaction where I heat up sugar and drive off the water, and I end up with black carbon. Okay, it's pretty cool. But how these are synthesized in nature, you're probably very familiar with photosynthesis and the idea that carbon dioxide, which is a gas, and water, which is a liquid, with sunlight can produce sugars. And so it's a pretty amazing reaction. And this is an example of a carbohydrate we call a monosaccharide. So it's a simple sugar. So you may have heard that when people talk about diets, that there are simple sugars and complex sugars. So we're going to start with the simple sugars, and there's many simple sugars, but they can generally be in these two classes, an aldose or a ketose, based on what functional group you have. So if you see an aldehyde, that's an aldose, and if you see a ketone group, that's a ketose. So this OSE ending is what we use for carbohydrates. So this is called an aldopentose because it's got 5 carbons, and this was a keto because of the ketone, but it's got 6 carbons, so we call it a hexose. So you're going to be oftentimes asked to draw all your aldohexoses, for example. Okay, or what's this one here? This is an aldotriose. Okay, so 3 carbons here. Now this is a really simple one called glyceraldehyde, and this is one of your simplest sugars because you have the aldehyde group on the end, and you have 1 chiral carbon. And so with this carbon, you have an OH group. Notice all of these carbohydrates have OH groups everywhere. Okay, so, and that sort of comes back to this idea that we have a hydrate of carbon. So hydrate is an H and an OH group. So OH and H, that's where water comes from. So we have D and L sugars. These are all chiral. These biomolecules generally are chiral. So there's a kind of left-handed form and right-handed form. We don't really use R and S very much with these biomolecules. We tend to use D and L. So a D sugar will be one where when you draw it in the Fisher projection like this, you're going to see it on the right side. So that means it's going to be a D sugar. And if it's an L sugar, it's just the enantiomer, which is flipped at that inverted at that chiral center. Now, by the way, D and L have to do with positive and negative. So it turns out that D-glyceraldehyde is also D-positive glyceraldehyde. And L-glyceraldehyde is levorotatory versus dextrorotatory. So that tells us about the specific rotation. So for this problem, there are 4 stereoisomeric aldotetroses. So let's draw all 4 possibilities. And we'll arrange them in pairs of enantiomers. So we'll have a D and we'll have an L. So first, for an aldotetrose, I need an aldehyde on the end. So I have C double bond OH. And a tetrose means I have 4 carbons. So 1, 2, 3, 4. And the last unit is a CH2OH. So I'm not told to draw any specific one. So I'm just going to draw OH groups anywhere. So I need an H and an OH group. Let's say I have this one. Is this a D or an L sugar? I think you guys remember D is where the last OH group is on the right side. So it's looking at these guys. These are D sugars because of those and because of this. So this is what makes it a D sugar, is that carbon right there. Now after that, I can draw the enantiomer of this simply by drawing its mirror image, which has all of those positions inverted. Okay, so this is the L form of this sugar. All right, so there's 2 right there. And then can you guys see the other 2 possibilities are diastereomers of these? So that would be, I can just arbitrarily pick the first one. If I do this, then I can't do the same thing here because I'll have this structure. So I'm going to modify it and do that here. All right, and then the enantiomer of that is where I just switch all those groups. Now, which one of these are D sugars versus L sugars? I think you guys can see my D sugars are here, and my L sugars are where the OH is on the other side, like that. So some of the monosaccharides you might be asked to memorize in biochem, at least I remember I was asked to memorize these, is these are all of the aldohexoses. So I would strongly recommend that you start memorizing them, but you don't have to do it for this course, but for biochem it's very helpful to do so. And one trick that my professor taught me, or TA, I'd forget, is that you sort of memorize the patterns. So when all of the OH groups are on the right, I sort of remember that as allose. A left, right is an altrose. Right, left, right is glucose. Left, right, mannose. And so I just go through that pattern, and then you can have it memorized pretty easily, actually. So, and it's sort of surprising how fast you can memorize these. Notice that these are all the D isomers. So these are the D sugars right here. And you can tell because it's the second to the last carbon where we look at the configuration. If it's on the right side of a Fisher projection, it's a D sugar. Same thing with these ketohexoses. You can see you have D sugar right here. These are all D sugars, but they differ in the other configurations. So OH on the left or right, and they're all called different things because they're all different stereoisomers. All right, so I don't expect you to memorize this. You'll have access to this to answer the questions, so feel free to just use it and learn some of the basics behind it. So first, draw and name the enantiomer of D-fructose. So they want you to look at L-fructose. So L sugars aren't on here, so I'm going to have to start with D-fructose and draw the enantiomer. So that means that I have a ketose. This part's not chiral, so CH2OH, but the rest of it I have to invert to get the enantiomer. And that means I'm going to have L-fructose, which means the OH right here is on the left side. So the relationship between D-fructose and D-glucose, I have enantiomer, diastereomer, constitutional isomer. Constitutional isomer, by the way, is that when you have isomers that are connected differently, whereas enantiomers are mirror images that are non-superimposable. These are enantiomers. And diastereomers are stereoisomers that are not mirror images. So this one and this one is these are diastereomers, or these are diastereomers, or these are diastereomers, or those are diastereomers. So any combination of this one with one of these is a diastereomer. Okay, so they're very similar, but their structures, their inverted centers are not completely opposite, like in an enantiomer. All right, so let's look up fructose and glucose, and they're both hexoses, so they have the same number of carbons, hydrogens, and oxygens. In fact, it would be C6H12O6, okay, because of that formula, CnH2ON. All right, so it's usually a 1 to 2 to 1 ratio for sugars. Okay, and so we have fructose, glucose, and I think you guys can see they're not connected the same because one's an aldehyde and one's a ketone. And also all of these OHs are different. Okay, so that means they're constitutional isomers. Cyclic acetals are more stable than acyclic. So for example, we've done a lot of cyclic acetals as protecting groups. Here's a regular hemiacetal. Okay, so you could use any alcohol. But if you can close the ring and have a cycle like this, that can actually be quite stable. And you've learned about this as a protecting group. It's really great because that can protect your aldehyde or ketone from reacting. And then you can use acid hydrolysis to turn it back into that group later. So that's a really important reaction. So we can do the same thing with sugars. Sugars are basically aldehydes with or ketones with OH groups on the end. So picture that this OH group on the ends can come back and cyclize. Now, which OH group it uses depends on what size ring is most stable to form. And I think you guys know 6-membered rings are the best. So it turns out that 1, 2, 3, 4, 5, 6, it turns out to be that last OH, the one that determines D or L, that last OH tends to be the one that can cyclize. So in this mechanism, we have some OH group down the chain. It attacks the aldehyde, and it forms a ring, a cyclic compound right here. So the idea is that we have a cyclization. So sugars do that as well. They go from their open chain form. They sort of bend around like this, and then you can have attack of one of the OH groups onto the carbonyl, and then you end up with the oxygen incorporated into a 6-membered or 5-membered ring. And 5 and 6 are the most common because of the reduced ring strain. That carbon-1 aldehyde carbon ends up becoming a carbon with an OH group because you can picture the attack on this carbon, the electrons go up to the O, and then it picks up a hydrogen from solution. So this is the closed form, and this is often the form we see in biochemistry books. You usually see closed cyclic acetal. And this is actually a hemiacetal, so it's important to remember. At this carbon, you have an OR group and an OH group, and that makes it a hemiacetal. And that'll be really important later when we look at properties of sugars. Now, depending on how the ring closes, I can have attack this way and have the OH sticking up, or maybe the aldehydes rotated downward. Maybe you guys can picture the aldehyde might be downward, and then you might have the OH group form on the bottom. So here it is on the bottom, and here it is on the top. And so you could have either form. And these, when it's on the bottom, this is called the alpha Anamur. And Anamur is the word we use for these two isomers. So we have it's sort of like tautomer. Okay, so we have this form, and we have this form, which is called beta. So beta is when the OH is up, alpha is when it's down. And this carbon that got attacked has a very special name. We call it the anomeric carbon. And that's because that's what Anamur gets determined is based on the attack at that carbon. Now, alpha and beta anomers can convert into each other by opening up and forming the open chain and then closing again in a different way to get the other isomer. So let's say that the chain closes up, we make the alpha form, and then in equilibrium there's some amount of the open chain form, so this one can open up again. These are reversible reactions, especially in acid we can open those up, and this open form can then close up again and turn into the beta form, for example. So we can have interconversion. And that process is called mutarotation. So you basically have open form going into alpha form, going back into open form, going to the beta form. And then you have some equilibrium. So you always have some amount of open form, but the ring form is usually more prevalent because of its stability. So you usually have alpha or beta Anamur. Drawing a Haworth projection from an open chain. These are called Haworth projections when we show the ring. And notice what makes a Haworth projection is that you're looking at it sideways, you're looking at the ring sideways, so all the groups are either up or down. So we've learned a lot of different forms. We've learned Fisher projections. This is a Haworth projection, and it's sort of like a chair a little bit in that there's groups that are up and down, right? But this is a lot simpler than a chair because it's literally up or down. They just really simplify it so that it's either straight up or straight down. So you don't have to deal with equatorial so much. So these are mostly dealing with just looking at whether groups are on the same side or opposite side. So Haworth projections, they're a different way of depicting a ring. So you could definitely also depict it as a chair. And so if I was doing that, I would say, here's the oxygen. And then at carbon 1, I have an OH group down. So I might do this as this OH here. And then that means I have an H equatorial up. I have an OH down, and I have an OH up. So here's my second one. And here's my third one is an OH up, which happens to be equatorial. And so, see, it's not very accurate. The equatorial ones look axial, right? And so it's not great for that, but it's really good because it does simplify the structures. And I'm running out of space on that last one. So that's sort of the chair form, but this is a Haworth projection, really simplifies things. To draw a Haworth projection, I usually lie a sugar down on its side and then I show the attack. Very similar to how this is done. So I take this molecule and I just rotate it down, so have it lie down on its side and then have it attack. And I think you guys will see how it's done. So Galacto Pyranose, I'm going to look at what that structure is. First of all, none of these, Pyranose is the name for a 6-membered ring, furanose for a 5-membered ring. Let me show you where that is. All right, so right here, we said this is a glucopyranose. That is a pyranose or 6-membered ring of glucose. This is the beta glucopyranose, okay? So pyranose just means 6-membered ring. So I want to make a 6-membered ring out of galactose, okay? So galactopyranose. So I look up here at galactose, and if I were to memorize this, I would say to myself, oh, galactose is right, left, right. Okay, so when I go down to make this one, and again, you don't have to memorize it for this quarter, but someday you may have to. So here's my aldehyde CHO, and I have right, left, right. So that was the pattern for galactose. So now what I'm going to do with this is I'm going to lie it down on its side and then I'm going to close the ring. Okay, so I'm sort of copying this form right here. See how carbon 1 here, I've laid it down to here. So carbon 1, I've laid it down to here. And then as I go around, I'm going to get to this carbon here, the anomeric carbon right here. That's going to be that carbon. So I have a CH2OH that I just sort of stick into the back. And then I have an OH group ready to attack this carbonyl and close the ring into a Haworth projection. So now the thing is, I want to make sure my stereochemistry at all these other centers is preserved. So to do that, anything that, so I laid it flat down. So anything that's on the right side is going to be down. So I'm going to make sure that this OH group here at carbon 2, this OH group is down at carbon 2, and at carbon 3, I have an OH group up because it's on the left side. So right, left, so that means up, and right. But this is actually this one. So I'm done. So right, left means down, up. Okay? And if you look at this one, it does the same thing. You have right, left, so down, up. Okay, so once I do that, now I can just close it. And if you want to, you can think of the mechanism, right? This comes in and this attacks and it goes like that. And the Haworth projection usually has the O sort of slightly to the right, and then the hexagon. And then this anomeric carbon determines, let's see, if it's alpha or beta, and they want us to draw beta, so that means this OH group happens to be up. So when this goes here and it picks up a proton, it happens to be up. when it closes. Okay, and the other one's an H. Don't forget to write your H's in. Now then we had down, up, up, and then the last one always looks like this, CH2OH. And that is it, okay? So that is how to draw a Haworth projection. And then here's an example of how to draw a chair, which I already worked through. So for practice, you guys could try these two problems. Just practicing open chain form, converting it to a closed Haworth projection, and opening it again, doing alpha and beta as well. And remember, you don't have to memorize these right now, but feel free to use them in order to practice doing these problems.